Hello, this is mathjazz from Almost Cool. I am here with an integration question that basically tests every integration technique that's standardly taught in a second semester calculus class. It was sent to me by a student this afternoon, and it is quite impressive. So here is the problem. We are finding the antiderivative of x squared minus 3x plus 8 over the square of x squared minus 4x plus 7. And we're integrating with respect to x. So we're going to find this antiderivative, and we're going to need every technique that we learn in a second semester calculus class. So first, though, we'll need to use partial fraction decomposition. We notice that not only is the only factor in the denominator an irreducible quadratic, but it is also a factor of multiplicity 2. So if we have a factor in a rational expression that we're trying to express in a partial fraction decomposition, if we have a factor that has multiplicity greater than 1, we need to represent that factor in the partial fraction decomposition as a denominator of every power up to and including the multiplicity in the denominator of the original fraction. So what that means is, since this thing is squared, we need to have one fraction where our factor is to the first power and one fraction where this factor is to the second power. If this were cubed, we would also need a fraction where the denominator is to the third power. And so on. So, but not only that, but irreducible quadratics, instead of using a constant like a, b, or c in the numerator, they need to have a line in the numerator. That is, they need to have ax plus b or cx plus d or so on and so forth. So I'll just put this on the screen, and maybe that will make more sense than the explanation. We need to have two fractions because the multiplicity of the factor is 2. One of those fractions needs to be the factor to the first power, the other needs to be the factor to the second power. And then, since this factor is a quadratic, an irreducible quadratic, we need to have, instead of just a and b as the numerators of these two fractions, we need ax plus b as the numerator of one fraction, and cx plus d to be the numerator of the other fraction. So already this is a tougher than typical partial fraction decomposition, and this is a long problem from here. This is only the beginning. But the good news is that if you can follow every step of this problem, then you can pretty much handle anything thrown at you in your integration section of your calculus classes. So from here, we need to figure out what the coefficients a, b, c, and d are. So first, we multiply out by the denominator of the fraction on the left-hand side of the expression, and we get this equation. Now, from here, we'll notice that there is only one term after we multiply this out that has x cubes in it. That is ax cubed. We don't have to do the whole multiplication out, but we can see that b never gets to be times a cube, and c and d never get to be multiplied by x cubed either. So ax cubed is on this side, the right-hand side of the equation, but there are no cubes on the left-hand side. So we know that a has to be 0, since there are no cube powers of x on the left side, and there's ax cubed on the right side. So knowing that, we can already substitute that a equals 0 into this equation to get a simpler equation, like so. This looks better already, because now we have no binomials times trinomials on the right-hand side. So from here, we get to keep going. We notice that b is the only constant on the right-hand side of the expression that gets multiplied by x squared. So we know that bx squared must equal the x squared term on the left-hand side of the equation, so b must be 1. And again, we can update our equation to take that into account. So it's getting better. We note also that d is the only constant on the right-hand side. Let's say that again. D is the only constant that is multiplied by x to the 0 on the right-hand side. So 7 plus d has to equal 8. But that means that d is 1. And, sorry, that might have gone a little quickly. From here, we can also cancel out the x squareds on each side. We know that d is 1, we substitute it in, so we have an 8 on the left and an 8 on the right, and they cancel. And we're left with just negative 3x on the left, negative 4x plus cx on the right, like so, which means that c equals 1. So we plug in that information. A is 0, b is 1, c is 1, d is 1, and we get this as our new integrals. We're going to split the integral. So we have the integral of 1 over x squared minus 4x plus 7. That's our first fraction. And x plus 1 over the square of x squared minus 4x plus 7. That's our second integral. So I'm just going to scroll back just once so that we can see our original integrand on the left and our two fractions on the right. A is 0, b is 1, c is 1, d is 1. And plugging those into this expression gives us what we have here. So we're going to solve each of these integrals on the right-hand side one at a time. The left-hand side looks simpler, so we'll start with it. And we're going to have to complete the square so that we can do a trig substitution. So from here, we look at the denominator, we complete the square, we get x minus 2 squared plus 3. And looking at that, we decide to do a trig substitution letting x minus 2 equal the square root of tangent of theta. We pick that because when we square, so the square root of 3 times tangent of theta, we will get 3 tangent squared theta plus 3, and we can factor the 3 out of the expression. So, this integral on the far left becomes the integral on the left side of the right hand of the equation. We plug in our dx and our square root of 3 tangent theta appropriately, and we get this that looks harder at first, but we will see that we get some cancellation. You know, the 3 comes out, the square root of 3 comes out, leaving us with a 1 over the square root of 3 as our coefficient on that integral. Tangent squared theta plus 1 is secant squared theta. The numerator cancels with the denominator, leaving us with a fairly nice 1 over the square root of 3 times the integral of d theta. Now we left the right-hand side integral, the right integral alone in this whole process. So now we come to it. And we look at it, and it looks hard. Oh, I guess we also took the integral of d theta to get this theta over square root of 3 as the answer, as the value of the integral on the left. This integral here, the integral of x plus 1 over the square of x squared minus 4x plus 7, we look at that and we think, well, let's try the same thing. We will complete the square, just like we did for the other one, and we will do the same trig substitution as on the right. One thing that we will have to notice is that we have x plus 1 in the numerator, but that's just x minus 2 plus 3, and we already have a substitution for x minus 2. So x minus 2 becomes square root of 3 tangent theta, and we add 3 to that. So we get this. And that looks pretty horrific. But we have addition in the numerator of a fraction, so we're going to try splitting the fraction. So from this expression here, we will split the fraction, we get 1/3 of the integral of tangent theta over secant squared theta d theta, and we get 1 over the square root of 3 times the integral of 1 over secant squared theta d theta. And that comes from this 9 and the square root of 3 and the square root of 3 all interacting with each other in interesting ways. But I double checked it. I'm pretty sure that I factored it out correctly. So from here, we're going to use some trig identities to simplify our expressions. So tangent theta over secant squared theta, that's sine over cosine over 1 over cosine squared. So basically there are two cosines in the top, a sine in the top, and a cosine on the bottom. That simplifies to sine theta cosine theta. The other one, 1 over secant squared theta, becomes cosine squared theta, d theta. So just some trig substitution, or trig identities there. And from here, the 1/3 integral of sine theta cosine theta d theta, we can do with a u substitution. So that's pretty nice. So we let u equal sine theta, du equals cosine theta d theta, and this integral here becomes the integral of u du, or 1/3 of the integral from u to u. The cosine squared theta d theta, we're going to use our double angle formula for cosine and turn that into 1/2 of cosine of 2 theta plus 1. So the 1/2 comes out, and we have the integral of cosine of 2 theta plus 1. Now we have something that we can handle. We know how to use the power rule on u du, and we know how to use well, it's technically a u substitution, but I'm sure we can see how the antiderivative of cosine of 2 theta is going to be 1/2 of sine of 2 theta. So from here, we can go and perform those antiderivatives, and we get this expression, theta over the square root of 3 plus u squared over 6 plus 1 over, make sure that happened correctly, yeah, plus 1 over 2 times the square root of 3 times 1/2 of sine of 2 theta plus c. And now we have to substitute all the way back to x's, or we have to back substitute. So first thing we notice is that if x minus 2 equals the square root of tangent of theta, then theta equals arctangent of x minus 2 over the square root of 3. So we can make that substitution and get rid of this theta over the square root of 3. U squared, well, u was sine of theta, so u squared is going to be sine squared of theta. And the next one, well, the theta, of course, again, is the arctangent of x minus 2 over the square root of 3. I distributed this 1 over 2 square root of 3. And now we just have to worry about the sine squared theta and this sine of 2 theta. But, so to do this, we're going to use the double angle formula for sine to get that sine of 2 theta is equal to 2 sine theta cosine theta. The 2 will cancel with 2 in the denominator of the fraction. We're going to combine the 1 over square root of 3 arctangent term at the front of the expression with the 1 at the back of the expression. So that'll be 3 over 2 times the square root of 3 arctangent of x minus 2 over the square root of 3. And from here, we need to draw a triangle. So this triangle will use our trig substitution. That is, that x minus 2 equals the square root of 3 times tangent of theta. Well, that's the same as saying that x minus 2 over the square root of 3 equals tangent of theta. And so tangent of theta is the opposite over the adjacent. So we have x minus 2 over square root of 3 represents the opposite and the adjacent side equals tangent of theta. We draw our triangle like so. Now, to find sine and cosine, which is what we have here, we need to find the sine of theta and the cosine of theta. We need to figure out what the hypotenuse is. We use the Pythagorean Theorem, and we get square root of x minus 2 squared minus 9. I'm sorry, minus 3. This should be a minus 3, because square root of 3 squared is 3, not 9. All of the subsequent 9s in this will really be 3s. Okay, so we find out what sine and cosine are. Again, this 9 and this 9 in the denominator are actually 3s. So we have the sine and cosine expression, and we plug that into our antiderivative, and we get, well, what we have here. We notice that we can have some cancellation. The square root of 3 cancels with the square root of 3 in the middle fraction, and we can cancel a square root of 3 out of the top and the denominator of the final fraction. Doing that gives us the expression that we see here. And this is our antiderivative, as complicated as it looks and as roundabout as it took to get here. Oh, again, the 9s in these are actually 3s. So thank you for watching this video. I hope that you were able to follow along and that you can use this to help practice your partial fraction decomposition and your trig substitutions and your U substitutions and your trig identities and basically everything that we need for an integral techniques test. Thank you, and have a great day.